Hi everyone, this is Darshan Senthil and welcome back to another video on differential calculus here. In this video, we're going to be discussing the derivatives of inverse functions. But before we go right into that, let's just do a quick recap of what an inverse function actually is, just so that we have a baseline from which to move forward. All right. So first point, inverse functions are two functions that undo each other, right? So what this means is that if you have some function f of x, right, it goes through a certain set of operations, right, to reach some output. So if I plug in some number in here, it's going to conduct some certain set of operations and give me an output. What the inverse function does is it will take that output, right? It's going to take that output and it's going to send it back this way. It's going to undo whatever my original function has done to it, and it's going to give me my input again, right? And this works both ways. So if the inverse function, the regular function is also the inverse of the inverse function, and vice versa. So the functions basically undo each other, right? Second point, this is that the input of one is the output of the other, and vice versa. And again, this makes sense based on what we talked about here, right? So if I plug some input into my original function, right, and then I run that through the original function, and then I run that through the inverse function, that same input is going to be what my inverse function spits out, right? So that's basically the idea here, and that's a really important thing to keep in mind, as a lot of key properties of inverse functions are built off of this idea. All right. So if this seems foreign to you, no problem. I have another video here that you can check out where I talk about these properties in depth. All right. So how do we take derivatives of inverse functions though? Because we don't have any real formula to work with. So here's where we start, right? So we start at this key relationship. F of f negative 1 of x. F negative 1 of x is basically just the inverse function, by the way, will equal x, right? And this relationship makes sense because if you plug the inverse function into the regular function, they should sort of cancel each other out and give you that x. So now that we have this relationship to work with, we can go ahead and take a derivative of both sides of this equation, right? And then once we've taken a derivative, we can get a formula for the derivative of the inverse function, which is something we can work with. All right, so we have d dx of so the derivative of all this in here and the derivative of that piece, that x right there, all right? So that's basically what we've got here. And now we can start taking these derivatives. So the derivative of x is just 1, right? And now the derivative of this is just a little bit more complicated. But as you can see, we have one function inside another, which is a composition of functions, which should immediately pique your interest, being a chain rule problem. All right, so we're going to use the chain rule here. So this would be the derivative of this whole thing, which I'm just going to annotate as f prime of f negative 1 of x, right, times, this is the piece we're really interested in, d dx of f negative 1 of x. And it's to get this piece that we actually start with this definition and not f negative 1 of f of x, because we need to use the chain rule to have that derivative of this, right? And that wouldn't happen if we use the other definition. So that's why we use this definition. All right, anyways, so now let's go ahead and just solve for the derivative of the inverse function, which is, after all, what we're really interested in. So we're going to have that derivative of the inverse function is equal to 1 over f prime of f negative 1 of x. Okay, so that's the formula that we'll be working with throughout the process of this unit. All right, so the nice thing about this thing actually is that you don't need to know what that is. So you really don't need to know what that is. So you don't need to know the exact identity of the inverse function. you can actually sort of reverse engineer just to find a value, and then you just take the derivative of the original function at that value. So you don't actually need to know the function itself, you just need to know what the value of the inverse function would be at whatever point. So why is this useful? Like you might just be thinking, why go through the trouble of using this formula when you can just go ahead and find the inverse using some method you might have learned, and go ahead and just take the derivative of that? Well, here's why. So this is useful when it's impossible to solve for the inverse. So for example, there are things like cubic functions, things like that. It becomes very, very tedious to solve for the inverse by hand anyways. So in those cases, it's really you can't find the inverse, let alone take a derivative of it. And it's also useful when you aren't given a function at all. And if you don't have a function, you have nothing to solve for an inverse of, and you have nothing to take a derivative of. So often in these kinds of problems, these appear a lot in the AP tests. So you might just be given like a table of values and a bunch of stuff with which you'll be asked to solve for the inverse of the derivative of the inverse function at some point. So yeah, the key thing to know about all these problems is it's usually going to be at some point. You'll rarely ever be asked to find the actual derivative of the inverse function unless you can solve for the inverse. But 99% of the time, it's just going to be you're finding the derivative of the inverse function at some point. Right? So that's just something to keep in mind. All right. So now let's do a quick example just so that we can go ahead and really nail down what's happening here. So given that f of x and g of x are inverses, okay, and f of 2 equals 9 and f prime of 2 is equal to 10, find g prime of 9, right? So that's just a quick example to check out. So first thing we're going to do is just go write out the equation. So g is my inverse, so I can just go ahead and say g prime of 9, right, equals 1 over f prime of g of 9, right, because we're evaluating the derivative of 0.9, so I naturally have my original function there. All right. Now, what do I do to find g of 9? Because my information only says what f of 2 is and what f prime of 2 is. So I don't actually know how to find g of 9. So here's the fun thing that you need to know. If you recall, we know that we said with inverse functions that the input of 1 equals output of other. Right? So what you plug into one function is going to be what naturally you get out of the other function. So by this logic, g of 9, right? So g of 9, we're plugging 9 into this. So since we're plugging 9 into this function, that 9 should be what we get out of the f. So, or let me put this way. So g of 9 equals some value, then f of that value must equal 9, right? Just based on what we did here. So what f of what is going to equal 9? Well, that's right in our given information. F of 2 equals 9. So therefore, question mark equals 2. So g of 9 equals 2. Right? So now we can just go ahead and take that a step further, and we can say that this would be 1 over f prime of 2. And what's f prime of 2? Well, that's 10. So our final answer is simply 1 over 10. Right? So this is kind of how these problems work. You're going to have to sort of follow this logic through, and just sort of, this step is really the hardest part to fix, because once if you just plug it in, you'll usually see this setup pretty easily. But this logic over here is what can usually trip you up a lot, because if you're not given this piece of information, it's natural to panic, but you just have to take a step and really see what's going on. So that's the end of this video. Thank you so much for watching. A practice problem video, like I said, is coming up soon, so stay tuned for that. But in the meantime, do like, share, and subscribe, and check out some other videos.